Okay, hi everybody. Now I'm going to talk to you about ANOVA for a few minutes. First of all, as I've said before, the ANOVA is a parametric technique for determining if you have significant differences among groups. And I don't know why I'm so taken with this study. It's never been done. This is a study that I've been talking about on headache reduction with the three different groups, three different treatments: aspirin, kick in the shins, or placebo. And this is my idea of what we might find on mean pain scores on a scale of 0 to 10. How bad does your head hurt half an hour after you've received the treatment? The placebo group says 6, the kick group says 4 as on average, and the aspirin group says 2. Now, as I'm sure you can appreciate, the farther these means are from each other, the more it seems that there's significant differences between treatments. Also, the less variation you have within each group, which we call error, the more obvious it is that there are differences between the groups. Let me say that again about error being variance within the group. Now, here we have someone who took a placebo and a group of people who got the placebo. Some of these people who just took a sugar pill had a substantial reduction in their headache pain score. And here they are like right around 4.3 or something. Other people who got the exact same sugar pill are up here somewhere in the neighborhood of 8. And just think about that for a minute. Something is obviously different here between this person and this person, but what that difference is, we don't know. That's why we call that error. Anytime you give a group of people a certain treatment and there's individual variation in how that treatment affects them, that is error. We have not controlled for whatever it is that's making that those people respond differently. Okay, that's a crucial thing for you to understand when you're thinking about ANOVA and what it's doing. Okay, now I'm going to show you a bigger picture of this. Okay, don't panic. I'm sorry that this slide is so crowded. But let's just for a minute focus on the graph. Here you have the same three groups, but I've also included a total group. This is all the subjects in the experiment if we were to put them all together. And basically what I said is the total mean would be 4, okay? And the total variance obviously is bigger than the variance in any one group because it's everybody in the entire study. Now, there's a little technical point here that I'm not sure that I'm even going to go into with you guys, but basically what you do in order to arrive at variance is to sum squared deviations from the mean. Why do you square the deviations? Because if you have people who are positive above the mean and people who are negative below the mean and you sum those, what do you get? 0. And that's why we square it. Anytime you square a number, it's going to be positive, and then you add it. So the sum of squared deviations from the grand mean gives you something called total variance, or sometimes, probably a better way to think of this eventually is called MST, mean square total variance. Then within group variance, you do the same procedure, but you take the variance within each group from its own mean. And that, as I already explained to you guys, follow this arrow, is error, okay? All right, so you also have between group variance, which we sometimes call treatment variance, which is n times the total variance. All right, now there's an important conceptual point for you to understand here, and it's simply this. If our if we were to compare the variance due to treatment to the variance due to error, we would be more inclined to say there was a significant effect of treatment if that number were bigger and if the error number were smaller, okay? So that's how you calculate the F statistic, which is what ANOVAs do. Okay, so let me go over this one more time. I want to make absolutely sure that you guys understand this point because it is absolutely crucial. An ANOVA compares the variance that you get from error, which is individual differences amongst people in the same group. It compares that number, whatever that variation is, to the variance that you get from treatment, which is given everyone's participating in this study, what's their total variation from the group mean. So the higher the number is for treatment variance, the more we know that treatment is having an effect because it's causing variance. The higher the number is for error variance, the more we know that there are just personal differences that we don't understand. And the ideal situation is that you have a big effect size. And that's the effect size in ANOVA uses the symbol eta squared, and it's just the sum of squares treatment divided by the sum of squares total. Okay, so the bigger your treatment impact is compared to your total variance, the more confident you are that there's a big effect of your treatment. All right, I hope that was clear. Of course, you're always free to read about that in your textbook, but this is one of those things that that I look back when I was in school that I didn't really grasp, and I did have an aha moment, and I was like, okay, that's a relief. Now I feel like I understand what an ANOVA is actually doing. But I do want to point out that an ANOVA leaves you with a mystery. Even if you run the ANOVA and you get a significant result, and it says, okay, we do know the F statistic is large, and it means that the treatment variance is higher than the error variance substantially. And so we know that treatment is having an effect, but what we don't know is where is that effect happening? What is the significant differences between the groups? And I want you to think of an ANOVA as a black box that either says yes, there are differences, or no, there are not significant differences. But you still have to open that box in order to look inside and see where the significant differences are. And that is why you do post hoc tests. So after you find that you have a significant F statistic, your ANOVA is significant, you do post hoc tests, which some of the ones that I'm sure you've heard of are Fisher's LSD or Tukey's HSD. Fisher's is the most conservative and Tukey's is the least conservative, but there are lots of post hoc tests at your disposal. But what they're doing is they're answering the question, now that we know we have a significant ANOVA, where are the actual significant differences? And I think, you know, if we were to look here, we would definitely say there must be a significant difference between aspirin and placebo. Look at that, you know, look at those distributions. But we would need to run post hoc tests to say that with certainty. And also, aren't you guys curious about kick versus placebo or kick versus aspirin? And that's what you would need to run post hoc tests to figure out.